I'm going to present Restart Rollback, this novel fault model for efficient TE replication. This is joint work with my advisors, Rodrigo Rodrigues and Peter Derschel. So TEs, or trusted execution environments, are hardware components that enforce the correctness of computation even in a malicious setting, so where the host is not trusted. Additionally, these components enable remote attestation, which means that a remote client, can establish a connection to the TE and attest that it's running correctly. Okay? And this can then be used to build a trusted cloud service like Azure. Now, in terms of the guarantees that TE provides us, we have confidentiality and integrity of the computation, but we do not have availability. This is because the TEs are highly dependent on their host for functionality, which means that the host can at any point shut down and break availability. And kind of a good solution to this is to replicate the TE. So if we replicate our service, even if one of the components crashes, we can then ensure that the other replicas get that availability. And this is something that's been done already. There's been plenty of research on replicating TEs to implement various services. Now, when we're replicating, we need to first we need a protocol to coordinate replicas to ensure that the system maintains correctness. And kind of the first step to this is to evaluate our model. Essentially, in what ways can our replicas fail? And this leads us to the question of what is the correct model for TE replication? And kind of the first step to this is to look at crash fault tolerance. So in CFT, we kind of assume that the replicas are running correctly and that the only failures that they can exhibit is becoming unresponsive or crashing. And this matches up with TEs. So the TEs have correct computation, so this in principle should work, and it does. However, if we then introduce persistent storage in the mix, things become a little more complicated. Because the persistent storage is not under the direct control of the TEs, and so the host OS can do all sorts of things to it. In particular, they can write state and rewrite state that the TE would like to preserve. Now, we have some mediations for this, namely encryption and integrity protection, which means that there are no arbitrary writes, and also by storing some integrity information inside the TE, we can make sure that they can't tamper with it while the TE is running. However, as we see in the example, if one TE is down, the host can then replace the persistent state with the cell copy, and if that TE then comes back up to life and starts interacting with the CFT protocol, we break correctness because the model doesn't account for this. Now, a way to solve this would be to use BFT, or Byzantine fault tolerance, which assumes arbitrary faults. And this would be correct, right? Because rollbacks are just a specific type of arbitrary fault. However, BFT mechanisms are very expensive. So to quickly recap, we have a situation where if we have persistent storage, CFT is not sufficient, and we can be exposed to rollback attacks, but BFT is very expensive and very intuitively does not match up with the guarantees of TEs, right? So our question is, can we somehow achieve a compromise and the best of both worlds by having the performance of CFT and the correctness of BFT? And our position is that yes, if the fault model accurately represents the TE's behaviors. Now, in this talk, I'm going to present our solution to this, which is the Restart Rollback fault model. Then I'm going to show how we can adapt existing CFT protocols to this new model. And then I'll present Teams, which is an example system that implements kind of an equivalent for cloud storage of what the TEs are to cloud compute. Now, in our model, we want to kind of think of what states our nodes can be in, and we can assume that they're initially correct, but if they crash, they become offline. And now when they restart, this is kind of the big question, how can we model this? And we say that the nodes are suspicious. So they don't actually know if they've been rolled back, but they know that they've restarted, and so that's the only situation where the rollback can have occurred, and that they don't know if their state is correct or if it's stale. Now they can then become correct by either verifying its state with other replicas or by actively recovering its state. Okay, so now we have a model for how these TEs behave and in what ways they can fail. The next step is to build protocols on top of this, and kind of a major building block in doing so is quorums. So a quorum is a subset of replicas required to execute an operation. And the way the quorums are kind of this building block is because we have some intersection properties of quorum. So here, if you can imagine on the left, the quorum is going to write the blue value. We want to make sure that another operation using a different quorum is going to see that blue value in at least one replica, right? And we need a quorum system for the restart rollback, or RR model. Now, the full derivation is in the paper, but there are a few important characteristics that are sort of different from our model. Now, let's assume in this replica set where all the replicas are running correctly, the first kind of big difference is we separate our quorums into two types. There are quorums for writing state and quorums for reading state. But we still maintain that intersection property that read quorums are going to intersect write quorums in at least one replica. Note that they're also differently sized, and this is kind of good because in this example here, read quorums are very small, and since read is usually the most common operation, this will mean that reads will be more performant. Now, because read quorums are so small, this also means that read quorums themselves may not intersect. This is a problem that we will need to solve at the protocol level. Now, at this point, all replicas are running correctly, but what if some of them have restarted? In particular, let's assume that the replica at the intersection has been restarted and actually rolled back. So this replica now holds stale state. This original read quorum is not going to have any replica that has the most current value. And the way we solve this is, since the replicas actually know they've been restarted, they can flag it as such in their replies. And so the read quorum knows it needs to scale up to include at least one correct replica in that intersection. Okay? So with these quorum systems, we can now adapt existing protocols. And kind of the general methodology for doing so is first to keep track of the suspicion. So we essentially, at restart, we flag all our state as suspicious, and we're going to progressively remove that suspicion from our state. Then we need to identify what different operations we're doing in our protocol, and in particular, when we're reading, we want to use a read quorum, and when we're writing, we want to use a write quorum. Now, the last little bit is to kind of deal with the split brain problem that arises from the fact that read quorums may not intersect. And this will be inherently protocol specific. And details for this are in the paper. So we've adapted two types of protocols, the distributed register protocol, which provides a very simple read-write API, and the CFT protocol is called ABD, the BFT protocol is called Byzantine quorums, and we've also adapted a state machine replication protocol, in particular Paxos, but there are others, such as Raft, or in the BFT space, PBFT and BFT Smart, and a myriad of others. With state machine replication, it's a much more powerful mechanism that can implement any sort of deterministic service. Now, we've evaluated our protocols against the different fault model counterparts, and here we can see the performance of the read-write protocols in these throughput latency curves. So here, at each point, we're increasing the load that we're exerting on the system and measuring the actual throughput and latency we're getting from it. What we see is, at some point, the system will be at capacity, so the latency will spike up, and the throughput will not progress any further. And what we see is that restart rollback actually accompanies CFT quite closely, whereas BFT maxes out quite early. And this kind of points us to the direction that we've kind of achieved our initial goal, right? We have protocols that are correct, so the RR protocols are correct, whereas the crash are not, but we don't have to pay this very high cost that the BFT protocols force on us. Now, moving over to Teams. So Teams is actually interesting because when we started working on this a long time ago, Teams was actually our main focus. So we wanted to kind of solve this problem of securing cloud storage. And kind of the model came as a solution to problems we were facing. But then we found out that the model itself was a bit more fundamental, but Teams is still a very interesting problem unto itself and serves as an example of how we can use these models and these protocols in practice. And kind of the problem is we want to kind of have an equivalent to cloud storage as TEs are to cloud compute. So we want to increase trust in cloud storage. And in particular, we want freshness, integrity, confidentiality, and a way to share our state among different clients. As a strawman solution, you could consider encryption. But encryption by itself does not solve all these problems. In particular, encrypted state does not ensure freshness natively, and there's no real mechanism for sharing encrypted state among different replicas without also implementing a key sharing mechanism. And kind of our solution is we're going to build a trusted metadata service with TEs using the RR model, and we're going to enforce these properties on the metadata, and they're going to translate over to the overall data. And so here the architecture of the system is like so. The client, when it wants to store a new value, is going to generate the metadata and encrypt the data it wants to write. It's going to write that encrypted blob to untrusted cloud storage, and the metadata will be stored in Teams. And the way we achieve those properties we wanted is first by ensuring freshness over the metadata. By virtue of the protocols that Teams is running, we get freshness over the data. By storing the hash in the metadata, we can get integrity. The encryption key gives us confidentiality. Having a policy over the metadata provides a mechanism for principal sharing. And we also store an ID, which is essentially a pointer to untrusted cloud storage, which allows the client to fetch the metadata and then go over to untrusted cloud storage and get the data. Right. Now, we've also evaluated Teams in a number of different scenarios. Here's just one. Here we have a client co-located with 3 replicas running Teams, and the other 4 are outside the data center. And we also are using Redis as our untrusted storage, which is also at 50 milliseconds. And looking at the latency plot, the first thing that pops out is, for reads, we essentially have no overhead. This is a virtue of having a local read quorum co-located with our client, which means the metadata access in this scale is virtually instantaneous. But we seem to have a 2x overhead for writes. This is actually not fundamental to the architecture itself. It's more of a consequence of the deployment. Since the write quorum is at the same distance as the untrusted cloud storage, we essentially have that 2x cost. However, different deployments are going to yield different performances. We also implemented 2 caching schemes over Teams, specifically for reads. So the first one is a name cache, which essentially stores a hint on the client for the name of the encrypted blob. This allows us to parallelize the accesses. In this deployment, it doesn't offer much gains. This is a virtue of the metadata access being so fast. So parallelizing that access doesn't actually gain us anything. But we also implemented a value cache. And here the client stores the whole value. And we just need to check the metadata to ensure that our cache is still fresh. So to conclude, I presented restart rollback, which is a model that precisely captures default behaviors of TEs with persistent storage, and thus ensuring correctness, and shown how we can intuitively adapt CFT protocols with similar performance. And we've built Teams, which kind of provides this analog to the confidential VM paradigm for cloud storage. Well, and now thank you, and I'll be happy to answer any questions.
Yoshi from UC Irvine. I have a question not related to the default model that you kindly presented, but I was really curious when you said the replicas know that it has been restarted.
Yeah.
I just want to know how that's possible.
So when the TE starts, it starts running, it knows it has started running. So essentially, if you crash the replica, it has to restart at some point. And by starting to execute the code, it knows it's starting again.
So do you have like some sort of like variable inside a T that kind of flips, like for example, like a flag that sets to 1 and because T is the only one who can access that data, you have assurance that T knows that it has been restarted.
Well, not quite. You can think of it, I'm spinning a new T with the same local persistent storage, and so it knows that it started running. So the code is going to have some entry point, so it knows at the beginning that it's starting anew, basically. Not sure if this makes sense. Because otherwise, if the T was kind of just halted by the host OS and then resumed, that's not really a restart. And there you still have the protection of your volatile integrity checksum that you have in the TE memory, right? And then you can detect rollbacks, basically.
I'm not following really sure. I can ask you a
Yeah.
follow-up question. I'll demand my back.
Any other questions? Okay, I think I'll ask some question there. So in your implementation that you did, right, you just like implemented on which TE, SGX?
Yeah, so we implemented all three protocols, or both protocols in the three fault models, all in SGX, yeah.
But would it work for any other TEs? Like, is there any requirement for the TE to follow?
No, so this is very general over TEs because they also have kind of this fundamental problem of leading with persistent storage. So we just use SGX for convenience, basically.
It should work for any
Yeah,
TE,
yeah,
right?
it will work for AMD, for instance.
We still have 2 minutes for questions. If you guys, anyone else have questions? Okay.
Hi there, Eric, Wisconsin Madison. I was curious if you investigated sort of specific optimal quorum sizes. I know it's interesting to say the write quorum be larger than the read quorum. Was there some specific observation about what are good sizes for that?
Yeah. So we actually were a bit conservative in our evaluation, at least in the comparison, because by changing the quorum sizes, you could actually have smaller quorums for reads, and and we made sure for that not to be the case, because that would be kind of an unfair comparison. But ideally, what you really want is what we showed with the teams. So you want your clients to have a local read quorum, so that the most common operation will be very fast, basically. Yeah. And that will inherently depend on your deployment, basically. Yeah.
Gotcha. Thanks for this talk.